kinds of information can we get from a molecular orbital diagram? You use the molecular orbital diagram to calculate what's called the bond order. And basically, a bond order of 1 means that you expect there to be a single bond between the two atoms. A bond of order of 2 means you expect a double bond to form between them, and a bond order of 3 means you expect a triple bond to form between them. So if you get a bond order that's greater than 0, you can predict that there's a stable bond between the atoms. Now, if your bond order is 0, then that means you don't expect that bond to be stable. Okay? How do you calculate the bond order? What you do is you assign electrons to orbitals just like we do for atoms. 2 electrons per orbital, 1 spin up, 1 spin down, okay, maximum of 2. And the bond order would just be the number of electrons in the bonding orbitals minus the number of electrons in the anti-bonding orbitals, and you divide that by 2. So let's illustrate that with this diagram. This is the molecular orbital diagram for a diatomic molecule. So this would be applicable, for example, for F2. F2, if you recall, has 9 electrons times 2. That's 18 electrons. Okay, atomic number of fluorine is 9. It's 1s2, 2s2, 2p5. Okay, 2 electrons in the core and 7 electrons in the valence shell. So let's assign those 18 electrons. We have 1, 2, 3, 4. So 2 in the 1s sigma, 2 in the 1s sigma star, and then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay? Now, if you look at these orbitals, you can say, let's look at the bonding orbitals. This is bonding, this is bonding, this is bonding, this is bonding, that's bonding. So you have 2, 4, 6, 8, 10 electrons in bonding orbitals. And the number of electrons in the anti-bonding orbitals are 1, 2, 4, 6, 8. So 10 minus 8 divided by 2, that gives you 1. The bond order for fluorine is 1, so we expect fluorine to have a single bond. Okay? Let's do the same thing for oxygen. Oops, I don't have oxygen. Let's try oxygen. Okay. What will be the bond order for oxygen? So let's do oxygen. Oxygen would be 16 electrons, right? 8 times 2. 1s2, 2s2, 2p4, right? 6 in the valence shell and 2 in the core for each atom. So 16 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Note that we're spreading out the electrons between the 2 pi orbitals before we pair them off. Okay? So let's look at our bonding electrons in our bonding orbitals. We got 1, 2, 3, 4, 5 pairs. So that's 10 electrons in the bonding orbitals. Okay? Electrons in the anti-bonding orbitals are 2, 4, 5, 6, minus 6. So divided by 2, that gives you a bond order of 2. We expect oxygen to have a double bond. But look, there's something interesting here. Okay? Even though we expect oxygen to have a double bond, look at this 2 unpaired electrons here. Molecular orbital theory, LCAO-MO theory, predicts that 2 of the electrons in oxygen are not actually paired. They're in separate pi orbitals. And one experimental evidence that supports this is the fact that oxygen is paramagnetic. It responds to the presence of an external magnet. So that's a property that we associate with unpaired electrons. Okay. Now, if you did nitrogen, you'll find that this nitrogen would have 14 valence electrons. So if you did nitrogen, you'll have 2 less, and so your bond order would end up being 3. What about He2? What would be the bond order for a diatomic helium molecule? Well, Helium, if you recall, has 2 electrons. 1s2 is the electron configuration for a helium atom, so He2 would have 2 times 2 or 4 electrons. Okay, so we assign the first 2 electrons in the 1s sigma molecular orbital, which is a bonding orbital, and then the next 2 electrons would be in the anti-bonding 1s sigma star orbital. So you have 2 bonding electrons minus 2 anti-bonding electrons divided by 2. That gives you a bond order of 0. So we don't expect the He2 molecule to be stable according to molecular orbital theory.